So today I'll be telling you about the paper characterizing the distinguishability of product distributions through multicalibration. And this is joint work with Putterman and Salil Vadhan. The question that our paper focuses on is that of distinguishing between distributions. So we consider the following hypothesis testing problem. Suppose we are given samples x1 through xk that are promised to be drawn from one distribution x0 or another x1. How do we decide which distribution the samples are from? First, what does it mean to decide? One lens that we could view this through is that of statistical limits. So what is the information theoretic ability to distinguish between the two distributions? Now this is captured by the total variation distance. In our paper, we instead look at the setting of efficient distinguishers. So we study distinguishers computable by small circuits. Before getting into our results, we need to introduce some relevant terminology related to distinguishability. So for statistical distinguishability, the quantity we look at is the total variation distance. So when I say statistical distinguishability, I just mean the total variation distance between the distributions is something. On the other hand, for computational distinguishability within complexity and cryptography, we study the following quantity called the advantage. So we study the advantage of distinguishing X and Y with respect to circuits of size S. So for every circuit of size S, we look at A, X, Y, C, which measures the difference in the probability between the circuit outputting 1 on X and the circuit outputting 1 on Y. We say that X and Y are S epsilon indistinguishable if for every size S circuit, the advantage is at most epsilon. On the other hand, we say that they're epsilon distinguishable if there exists a circuit of size S with advantage at least epsilon. And we'll call this a distinguisher, particularly when epsilon is constant. One thing to note between the relationship between statistical distinguishability and computational distinguishability is the advantage can never be more than the total variation distance. Indeed, this is capturing how the statistical distinguishability is measuring the difficulty of any approach at distinguishing between the two. When we're looking at distinguishing between distributions, one of the core things we care about is the number of samples it takes to distinguish x0 from x1. Let's first study this within the statistical case. In the statistical case, the number of samples we need is the inverse of the Hellinger distance squared. So the ability of an algorithm to distinguish is captured by the total variation distance. And the total variation distance is closely related to another notion of distance called Hellinger distance, which allows us to capture the number of samples we need. So in the statistical setting, there is some distance measure between x0 and x1 that's capturing how many samples we need. Let's turn to the computational distinguishability setting. Before our work, there was no instance optimal characterization. So as I'll describe in a few slides, there were some characterizations that were optimal for some x0 and x1. But what we really want is a characterization of k that depends on the distance between x0 and x1 and will be asymptotically optimal for every pair of x0 and x1. So now to go to our results. What we do is we reduce the computational distinguishability of x0 and x1 to the statistical distinguishability of some x0 tilde and x1 tilde that are computationally indistinguishable from x0 and x1. And that's what I'll mean by this approximate notation throughout the talk. Also, if we're given explicit descriptions of x0 and x1, it's possible to efficiently compute x0 tilde and x1 tilde. So let's say you want to understand how many samples you need within this efficient circuit setting. You tell me x0 and x1, you can compute these and compute something, which is this. So we prove tight instance optimal characterization of the sample complexity of efficient distinguishers. And the sample complexity is given by the inverse Hellinger distance squared of this efficiently computable x0 tilde and x1 tilde, which look similar to x0 and x1. Our proof relies on the multicalibration theorem. This is a result from algorithmic fairness, so it may seem surprising that this is going to help us in a question related to cryptography and complexity. But this is part of an ongoing line of work that is bridging this multi-calibration theorem and fundamental results within graph theory and complexity theory. So here's the roadmap for the rest of the talk. First, I'll go over the main theorem and an alternative characterization of this main theorem. And then I'll go over the multi-calibration theorem and this variation of the multi-calibration theorem that we proved that will lead us closer to the setting of distinguishing between distributions. So our main theorem is as follows. For every pair of random variables, x0 and x1, and every pair of parameters s and epsilon, there exists random variables, which are efficiently computable, such that for all k, first, x0 is epsilon indistinguishable from x0 tilde by size s circuits, and the same holds for the 1 variables. Second, x0 tensor k and x1 tensor k are total variation distance of the tilde variables indistinguishable by circuits of size s. And this tensor k, I don't mean anything complicated here. I just mean take the product distribution of x0 taken k times. So to sample from this, you sample independently from x0 or x1 k times. The more surprising part of our results is the following. x0 and x1 are also total variation distance of the tilde variables distinguishable by circuits of size s prime, where s prime is equal to s up to polynomial factors. So this characterizes the distinguishability of product distributions, and by that we mean the k samples of x0 and x1 by the statistical distance between very related random variables. Finally, I won't get into this in the talk, but this above also holds with x1 tilde set to x1. So why might we want to only have one intermediate variable? So there are some settings, such as when x1 is uniform, that have special meaning when we're looking at computational indistinguishability. So when x1 is uniform, computational distinguishability is measuring pseudo-randomness, and setting x1 tilde to x1 allows us to study other relevant notions of distance when we're looking at the number of samples that we'll need. And the circuit size increases slightly as well, but this is only by a polynomial amount, so it still provides a characterization. I'll now present an alternative characterization of our main theorem. So in the setting of statistical distinguishability, by characterizing the distinguishability in terms of total variation distance, we got a characterization of the number of samples we need in terms of Hellinger distance. And this characterized the number of samples. So what we're going to do now is define something called the pseudo-Hellinger distance, which is going to provide a tight asymptotic characterization of the number of samples we need. So let's define the pseudo-Hellinger distance as follows. So the S epsilon pseudo-Hellinger distance between x1 and x0 is the smallest delta such that there exists related random variables, x0 tilde and x1 tilde, that are indistinguishable from the original variables, and also such that their Hellinger distance is at most delta. And with this characterization of our theorem, we see that k equaling theta of inverse of delta squared, so the inverse of the pseudo-Hellinger distance squared, is a computational analog of the statistical setting where we had k equals the Hellinger distance squared inverse of x0 and x1. Before I proceed, are there any questions? Okay. So now we'll be describing the relationship to previous work. So previous work on computational distinguishability by Halevi-Rabin, and then whose parameters were improved by Geyer in 2022, proved that if x0 and x1 are delta indistinguishable for size S circuits, then x0 to the k and x1 to the k are this 1 minus delta to the k plus epsilon indistinguishable for circuits of size S divided by poly k 1 over epsilon. So why is this bound meaningful? It mirrors a statistical bound as well, which is that of the total variation distance of the k product distribution scales is at most 1 minus the total variation distance to the k. Now, This is great, and it's optimal for some settings of x0 and x1. However, this leaves a few things to be desired that we address in this talk. So first, this is not instance optimal. So there are examples of x0 and x1, such as this is not tight. Second, a computational analog of the total variation distance is missing. What do I mean by this? So in the statistical setting, the total variation distance captured exactly how well can any approach do at distinguishing between the two distributions, and we want some characterization according to that here. And third, this doesn't tell us tightly asymptotically how many samples do we need to distinguish with constant advantage. So going back to the roadmap, I'll go up to the first step and describe multicalibration, which is a fundamental result in algorithmic fairness. Multicalibration says the following. For all randomized functions g over the hypercube 2, 0, 1, and all distributions x on the hypercube, and all parameters s and epsilon, there will exist a partition into k components where k is order 1 over epsilon. So very small amount of components such that for every part of the partition except for 1, and let's call that 1 p0, g is epsilon indistinguishable from its expectation over pi with respect to this distribution x by size s circuits. So we can break our function into a few parts such that each is indistinguishable from its expectation. We have one possibly distinguishable part called p0, and this is going to be at most an epsilon fraction of the domain. Now, lastly, and possibly the most surprising part of multicalibration, is that this partition is efficiently computable. It's computable by a circuit of size s times poly 1 over epsilon. So what are the trade-offs here? So we have size s circuits that we want to distinguish with respect to, and that contributes to our partition's complexity. And we also have epsilon indistinguishability that we care about, which contributes to the size of the distinguishable part and the complexity of the partition as well. To give an illustration, so we look at a function and the values it assigns to different different components of the domain. We break it up into small parts, and we look at the expectation of the function in each part of the domain. So for example, in this partition piece 1, mu1, or the expectation, is 0.4. And the multicalibration theorem says it's g in this partition is epsilon indistinguishable with respect to size s circuits from this expectation. To briefly give the more formal version of the theorem, so we have epsilon indistinguishable of x, g from x and mu, where mu is the expectation. And by having an efficient circuit, it means we have a circuit computing the pre-image of each of the k components of the partition. And this is of size s times poly 1 over epsilon. So the multicalibration theorem as presented so far is for distinguishing a function from its expectation. In our setting, we're focused on distinguishing two distributions from each other. So we know that our sample came from one distribution or another, and we want to see what can the multicalibration theorem tell us about distinguishing between these two distributions. So to go from functions to distributions, we can use this lemma of Cassandra, Dwork, and Vadhan, which they used in the context of complexity theoretic implications of multicalibration. So if G is epsilon indistinguishable from its expectation in a part of the partition, and this expectation is taken with respect to a distribution x, then we can say that x in this partition, where the G function equals 1, is epsilon prime indistinguishable from x in this partition where the G function equals 0 with respect to size s circuits, where epsilon prime and s prime depend on epsilon and s and are just slightly smaller. So we can go from a function being indistinguishable from its expectation to saying two random variables are also going to be indistinguishable. So multicalibration compares a function to its expectation. So to compare distributions, the general roadmap will be, we choose a g and an x such that where gx equals 1, we get the random variable x1. And where gx equals 0, we get the random variable x0. And we define x this distribution we're taking the expectation according to, so that x, and also x0 tilde, so that to sample from x0 tilde, we first sample a part of the partition according to the weight that x0 gives it, and then we sample according to the same this distribution x that we've defined, and likewise for x1 tilde. So what do we gain from multicalibration? We gain this different characterization of multicalibration for distinguishing between distributions. So for every x0 and x1 and parameters s and epsilon, there exists a low complexity partition function for m equals order 1 over epsilon. And low complexity here means that it's computable by circuits of size s times poly 1 over epsilon, though I won't be explicitly stating it here. And m is order 1 over epsilon, so there's very few parts here. And there also exist random variables, x0 tilde and x1 tilde, that are efficiently computable given descriptions of x0 and x1, satisfying the following. x0 tilde is epsilon indistinguishable from x0, and likewise for the 1 variables. If we look at the weight that x0 assigns to every part of this partition that's low complexity, it equals the weight that that x0 tilde assigns to every part of the partition. And the same holds for the 1 variables. And I'll be giving an illustration of these properties in just a moment. And finally, in every part of the partition, x0 tilde and x1 tilde are identically distributed. So we'll directly be taking the x0 tilde and the x1 tilde given to us by multicalibration applied with a specific g and x. Are there any questions so far? Mm-hmm. Mm-hmm. Yeah, that's a good question. So the only way that x0 tilde and x1 tilde will differ is how much weight they assign to each part of the partition. So here's an illustration. Let's say we're distinguishing this x0 and x1, and suppose that our partition is going to divide each of their domains into 4 parts. So I've drawn the probability density functions here. They don't need to be continuous parts, but for illustration, let's suppose they are. First, we have epsilon indistinguishability of x0 and x0 tilde. Next, we have that x0 and x0 tilde assign the same mass to each part of the partition. The third, we have that within each part of the partition, they're identical in distribution. So we see what's going on here a bit because this function is lower down than the other one, but they look the same once you condition on lying in that part of the component. So we combine x0 and x1 equally, sort of, and make sure that each partition part has the same weight as the original variables, so that all the difference between x0 and x1 is really lying in how much weight are we assigning to each part. Now I'll go into the proof overviews. So first, let's take the x0 tilde and x1 tilde that the previous theorem gave us. So by that previous theorem, we have indistinguishability of x0 and x0 tilde by size s circuits already, and the same for the 1 variables. So we're already done with this first point. Now let's focus on the second point here. So the second point is indistinguishability of x0 and x1 to the k. This is going to follow via a rather standard argument, a hybrid argument. So we have that x0 tilde is epsilon indistinguishable from x0, and the same holds for the 1 variables. So there's a standard method in cryptography and complexity to amplify this to distinguishability of product distributions. And we'll just follow that general method. And we'll use that the advantage of any efficient distinguisher is upper bounded by the total variation distance. Now to get to the possibly more surprising part of the result, the second part here, the distinguishability. Let's first start with a related problem, which is that of distinguishing x0 tilde and x1 tilde. So this is just part of the proof, but at the same time, this is a natural thing to do because once we have x0 and x1 efficient, or we have explicit descriptions, we can efficiently compute x0 tilde and x1 tilde. Let's start with this problem. Consider an x that's sampled from either x0 tilde or x1 tilde. and let pi be the part of the partition that x is in. So for example, this part here. Now, our multi-calibration theorem for distinguishing told us that once we look in this partition and look at the distribution of x0 tilde and x1 tilde, there's no information to gain from the sample besides the label of the partition, because the functions look identical once we condition on being in the part of the partition. Granted, each of the variables is going to have a different probability of falling within each part, but once we're in there, there's no information to gain. This will start to give us a recipe for optimally distinguishing between x0 tilde and x1 tilde. For each sample seen, we compute the part of the partition that the sample's in, and we see if it's more likely to have come from the x0 tilde variable or the x1 tilde variable. And that's really the best we can do, because that's all the information we get from the sample. For example, here, when we're given this partition, sample from this partition, the top is supposed to be gray and the bottom is green. The colors, yeah, are better seen here. So the bottom, if we look at the mass here within the bottom variable, bottom drawing, we see that it's greater than the mass at the top. So we output 1. More generally, when we have k samples, we're going to keep a running product of the following form. We're going to call this the likelihood, or the likelihood ratio. So we look at all the samples and we compute the ratio between the probability that this partition was obtained by sampling from x1 and the probability it's obtained by sampling from x0 tilde, which are tilde variables. And why is this the right thing to consider? Well, we argued that this is all the information we can get from the partition. So this is the likelihood ratio test. So this is a fundamental thing studied in statistics, and it's known to be the optimal distinguisher. The optimal distinguisher is going to output at least 1, or it's going to output 1 if this is at least 1, and else output 0. It's the likelihood ratio test, and it's known to be the optimal distinguisher. Therefore, it has advantage equal to the total variation distance of x0 tilde to the k and x1 tilde to the k. So why couldn't we have done this in the first case when distinguishing between x0 and x1? Why couldn't we have considered the likelihood ratio test? Well, it's not known in general that this is something efficiently computable, and we want our distinguisher to be encoded by small circuits. So let's argue why L is encoded by small circuits. So L is encoded by small circuits because P is encoded by small circuits based on this multi-calibration theorem for distinguishing. And P also has a small support. It's supported on order 1/epsilon parts. And so when we argue about the circuit complexity of L, given that of P, we can get that it's efficient. It's poly in S. Finally, we cared about distinguishing x0 and x1, and this is where we go back to the multi-calibration theorem. So the multi-calibration theorem gave us random variables x0 tilde and x1 tilde that were epsilon indistinguishable from x0 and x1 for small circuits. So if we have a distinguisher for the tilde variables, we have one for the original variables up to some epsilon loss, small loss. So to conclude the talk, we proved the tight instance optimal characterization of the sample complexity of efficient distinguishers. So if we want to distinguish x0 and x1, we can efficiently construct x0 tilde and x1 tilde such that the sample complexity of distinguishing between the two is given by the inverse Hellinger distance squared of the related variables. So this is a computational to statistical setting. The key technical ingredient was multi-calibration theorem for algorithmic fairness. And I think for natural open problems, there are many other things that could be explored within the lens of multi-calibration in terms of applications to complexity in cryptography. Thank you for listening, and please let me know if you have questions.